Okay, we're recording now. Okay, let's look at some principles of flight in terms of structural components and control of an aircraft. Okay, we've got the small aircraft, single engine aircraft. If it was twin engine, you just add another engine on there. And you just change its positioning. So let's look at the front here. You got this green here, protrudement, which is the spinner. Then you got the props on there. Then you got this cowl. This cover here is what covers the engine. Okay. Then the struts. We got also the strut from wing to the fuselage, which we'll call the wing strut. But also on both, it's also on both sides. Then obviously you've got the wing. And on the wing, we're gonna break it down a little bit more as well and see what other sub components we have. Then you got the landing gear. Okay, this one has got one in front, two at the back. Okay. Then you have here, these devices are now for the control of movement. You have we have the aileron. Then just next to it, we got the wing flaps. These here will also these are moving devices. Again, on the other side, you got the aileron, and then you also have the flaps. Okay, then you got what we call the dorsal. Okay, just strengthening the main tail. And we normally, this tail here, we also normally call it a fin, dolphin, a fin. Then we also have the tail plane running right across. And then at the back here, we also got moving devices, components or devices. This will be the elevator. So we'll all have a look and see what part they play. Then you got the rudder at the back here. Okay, this again is vertical. So the rudder is vertical, everything else is horizontal. Then we got from all the to the end there, we got the fuselage. Okay. Have I left anything else? The windscreen, the pilot is inside, the passengers also sit inside. So it's part of the fuselage. You got the cabin and the cockpit as well. And then also on the fuselage there somewhere, you also have the baggage compartment as well. And the fuel is normally put in the wings here. Now let's look at a bigger aircraft in three views. When you're facing the aircraft, what will be most dominant is the wings, the fin, but you also see the tail planes either side. Then you've got the two engines. And of course, what you can also see here is the front end of the fuselage. Now, when it comes to aircraft identification, this front end of the fuselage, which is sometimes referred as nose, might give you an indication of what type of an aircraft it is. Airbus fuselage, they'll look almost identical. Same with and different from the Boeing family, etc., etc. So it's another way of this number of windows as well. They'll tell you also a lot in terms of the aircraft types, but also in terms of capacity as well. Let's look at it from above. We see here now, these here, they've got what we call leading edge slats with an A. Mariela, it's with an A, not a U. Okay, and then at the back here, you've got the aileron. Then this here, and at the top of the wing, just slightly at the top of the wing here, these are called spoilers. Spoilers. So they're there to spoil something. Then here you've got the flaps as well, either side. Then you got the tailplane, then you got the elevator, again the flight deck, and the radome. This nose here, they call it the radome. This is also where you find, I think that's where you'll find the area for the weather radar and stuff like that in front of the aircraft. Now let's look from another side view. You got the rudder, you got the fin, you got the fuselage. Then, okay, and there somewhere you got the emergency exit, the main doors, back and front. Then you got the undercarriage. Then you got the nose gear. Okay. So all these here, the leading slats, they can move down or up or flat. In flight, they are normally, in level flight, they're normally flat. These flight spoilers also, they are flat on the wings. This will help the aircraft brake. So once you've landed, you can put the flight spoilers to assist with creating what? What are you
Drag.
drag? Yes, it will increase drag, and then it will also assist with slowing the aircraft. Okay. Then the ailerons again are for turning. Then the flaps also can go level, up or down. If they are down, what are they going to increase?
The angle of attack.
They can increase the angle of attack, but they can also, for landing, they can also be used for again more drag as well. Okay, so normally most of these jet engine aircraft, they're now more or less two engine. They used to be four, they're now down to two very efficient two aircraft. Two engines, except for the Airbus 380. What do you think are the advantages of having two engines?
Less weight, so fuel efficiency.
Yes, they tend to then less weight, so it means also less weight also equals to fuel efficiency. But not only that, it also means you can increase the load as well, in terms of passenger, in terms of cargo as well. When we see airliners, we think mostly of passengers. That's not where the money is. Their money pretty much is is mostly in cargo as well. They carry a lot of cargo. Good thing with cargo, cargo won't complain, cargo won't ask for tea, cargo won't ask for whiskey. Cargo will just sit as cargo. And you can just pile one on top of the other. Mhm. Okay. But what we must also understand, when they moved from 4 to 2 engines, there were some calculations that had to be made. This is for Mario's information. The calculation, the efficiency of engines were not as good as this modern day 2-engine aircraft. So with 4 engines, and except for the for the DC-10 and MD-11, they had 3, 1, 2, then another third one at the back here. But in most cases, most aircraft had 4. So they would also think in terms of, if you lose 1 engine, you got 3 engines. So it means your chances, if you are flying over the high seas, your chances of then diverting to a destination which is on land are much higher. Okay, so you lose 2 engines again. They would say, okay, what are the chances if, God forbid, there's fire on all engines? Then your chances are less, but you could probably still make it. But what they've done with these 2 aircraft here, with these 2 twin-engine aircraft, is they made calculations. If you're flying over the high seas, how far can 1 engine take you? Now, when they did the calculation, they'll take a radius of most of the routes and say, this here at any part of the high seas, 1 engine should be able to take you to the nearest aerodrome on land. So far, so good. So it was not just random and wake up one morning and say, hey, let's just take off 2 engines and see what happens. If that had happened, a lot of SH would easily happen. Okay. They used to call it ETOPS and stuff like that, but this is no longer a factor now. It's been tried and it works. Unless, obviously, you have both engines on fire. Again, we're not saying it doesn't happen, but the same way we would say an 80-year-old grandmother could have twins. So those are also the equivalent in terms of possibilities. But we cannot never rule it out. One day it might happen. Chris, when do you think you'd most likely Nigerian grandmother? Of course not. She would have triplets if she was Nigerian. Now, Chris, when is it most likely that you might lose both engines?
I don't know.
Oh, come on, you try. You've mentioned it before excitedly. This is one of your favorite areas.
During turbulence.
No. Think again.
Flying
I've
through
just lost my. Oh, okay, I've got it now.
Flying through volcanic ash.
Volcanic ash, yes. There's a
Okay.
very good chance there you might, yeah. And also, if something goes wrong with fuel calculations, which don't happen very often, I think there is now some some stopgap measures that are taken so that it doesn't happen. Because it actually happened once. I think when they started having, it was again these two engine aircraft, and then the fuel calculations had to be slightly different. And the person who was calculating, in America they use gallons, and everywhere else they use liters. So it was they used liters instead of gallons, or gallons instead of no, they used gallons instead of liters, which means the aircraft didn't carry much fuel, and it ran out of fuel. So they just couldn't understand how that had happened. Then eventually they realized that they'd been a miscalculation that way. Okay. So these components here are designed to be aerodynamically stable, because that's what we want. We want a stable aircraft. If it flies one day, it's flying upside down, then the other day it's flying sideways, then it's not going to be comfortable for the passengers. Okay, this means that an aircraft will automatically return to a stable altitude when affected by atmospheric conditions. So it can get affected by sudden, like wind, gas, turbulence. Okay, if it's been affected that way, the aircraft should adjust itself just to come back to a position of stability again. If it didn't, then it wouldn't be an aircraft. Call it something else. And no one would want to fly in it, because it means if you've got a gust to the left, it will just keep spinning now around that wind gust. If it was turbulence, it will just throw you up, 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 and doesn't come down sometimes. And when you come down, I don't know, it's with a big bang, and then it starts spinning, and then it starts doing a lot of things. So what aircraft are designed to do is whatever happens aerodynamically, they will come to a stability. Let's look at all the possible stability that we expect from an aircraft. Aircraft is flying straight and level. Okay, everything is equalized. Then all of a sudden there's an upward gust of wind. So obviously the nose will pitch up naturally. This will include, the angle of attack on the tailplane increases. Okay, the angle of attack on here increases. Lift is produced on the tailplane, and then the tailplane will automatically rise. So the gas is on there, but the reaction is now behind there. Okay, it will rise. Once it rises, it will put the nose down. It's rising, so the nose will go the opposite direction, and then the aircraft returns to stability. That looks like some people I know on a Friday night. Somehow they stuck a little bit, then go back to stability, but not for long. Let's look at another scenario. Relative airflow is going in, everything is good. Then all of a sudden there's a gas from the left, sorry, from the side. So the aircraft will tend to turn in the direction of the gust. So the aircraft will then generate an angle of attack, which creates lift on the fin, and this will then make the aircraft regain its directional stability again. Let's look at another one. Aircraft is flying straight, gust from the right underside. The aircraft roars left and slips. So when an aircraft is turning, there are two things that can happen. An aircraft can then either slip if it's going outwards. I'm trying to figure out how to for you to visualize this. Let's go back to motor vehicles. If you are turning, right, it is especially a high speed, the aircraft is turning, but it is also sliding. That's if it slides out, that's a slip. If it slides in, yeah, that's a slip, yeah. So the aircraft here is turning left, but it's also sliding. Mhm. So as it does that, this creates drag now on the upper surface of the aircraft. Then the aerodynamic force then rolls the aircraft back to horizontal. Again, now you've got the directional stability, the turn. You now recover from the unwanted right-hand turn, and also from the slip as well. Now let's look at the axes, not X, but axes. Each one is an axis with an E is when we combine any of the axes. The aircraft can yaw, which means it just can go round. Level flight. It can roar, which means it can turn left or right. Then it can pitch up or pitch down. Okay, those are your roar axis. Sorry, those are your axis of movement. Yaw or roar, which means left or right turn. And again, remember, this can also be associated with slips as well. Then also pitch up and down as well. Okay, those are the control panels that normally the pilot uses to control those axes. Now let's look at the roar. So both sides you've got the aileron. Okay, control column turned left. The left aileron then will move up, and the right aileron moves down. Okay, so the aircraft is then forced to roll to the left. Okay, if you want to do the opposite, then you'd also do the opposite of that if you want to turn right. So what is happening here? Lateral movement of control column moves the ailerons. This modifies the angle between the chord line and the relative airflow. That's increasing the angle of attack. The more lift is generated on this wing, causing it to roll left or right. You use the rudder here. The left rudder pedal here is what moves this elevator here. Left rudder pedal is pushed, rudder moves to the left, then the aircraft will yaw to the left. Let's see what is happening aerodynamically. Movement of the rudder pedals moves the rudder. This locally modifies the angle between the chord line and the relative airflow. That's increasing the angle of attack. This lift on one side of the fin causes the yaw to the left or vice versa. Now let's look at the pitch. Control column is pushed forward, then the elevator moves down, and then the aircraft pitches nose down. Let's look at what's happening here. It's up. Again, the chord line has been adjusted. Longitudinal movement of the control column moves the elevator. This locally modifies the angle of attack between the chord line and the relative airflow. That's increasing the angle of attack. The lift on the tailplane causes the aircraft to pitch up or down, depending with whether you want to climb or to descend. So let's look at the stability components. Wings, you can use them to roll. Tail plane, you can pitch up or down. Fin is to yaw around, that is the turn around the axis at level of flight. Directional control, aileron, you roll. Elevator, you pitch. Rudder, you yaw. Any questions before we go on to a bit of helicopters? There's quite a lot here on helicopters. We're not going to need to know all of it. What we just need to know is helicopters tend to do things differently. Okay. Looks like we're all good to start talking about helicopters. So you've got the air cabin there. Obviously, you have the airframe as well. Again, look at the design as well. Whether you like it or not, that's how it's designed. Okay. Then you've got the main rotor system here. But again, look at this rotor here, the rotor blade. Again, it's designed the same way as aeroflow as well. Okay, as an aerofoil. Then at the back here, you've got the tail rotor system. This is for directional now. If you hit a tree with this, some S will happen. If it stops running, some S will happen. This thing might go into an automatic spin. Then there's transmission. So you have to transmit between what's happening in the front here and also at the back here. Then you got the landing gear. Then you've got the power plant, which is just the nice way of calling an engine. Okay, and that would be your power plant. Okay, and then there is also what we call anti-torque pedals. We'll see what the torquing can do. And then there is the cyclic as well, the kind of looks like a joystick. And then your throttle is just on the side here. Helicopter pilot will use 4 basic flight controls. The cyclic pitch control, the pitching up and down, the collective pitch control, the throttle, which is usually a twist grab located on the end of the collective lever, and the anti-torque pedals. The collective cyclic controls the pitch of the main rotor blades. So these rotor blades also can pitch, okay, in different angles as well for climb, descent, and then level flight. They're straight like that, rotating. But what is then stopping the helicopter from when the rotor blades are rotating? What stops also the helicopter to follow the rotor blades? Okay, so in opposite direction, you've got the anti-torque, which goes in the opposite direction and then stabilizes the flight. If you understand it, you understand it. If you don't, nobody's going to kill you for that. Okay? Absolutely not. Okay? But just imagine the rotor is going round. Why is the helicopter not going round and round with the rotor? Okay? So there's something that's working in the opposite direction, and that is the anti-torque. Power plant, typically engine drives the main rotor through a transmission and belt of centrifugal clutch systems. The anti-torque rotor is driven by the transmission. Okay, so there is the torque. It's in the opposite direction. Okay, and the anti-torque rotor produces thrust to oppose torque, preventing helicopter from turning in the opposite direction of the main rotor. So there is the tail rotor thrust to compensate for the torque. So this is what this one here at the back is doing. Okay. Then you look at the more modern types of helicopters as well, where they do not have this as well. Anti-talk, again, there's an example there of an anti-talk system. Now, if you look at this one here, it doesn't have. So these are no talk systems. This is a new concept. Still provides some directional control, but again, using what we call the Coanda effect. I'm not going to go into too much detail of that, to be honest. All you need to know is NOTA replaces the need for an anti-talk at the back with the same effect. Okay. So it's got thrust and vertical stabilizers. Let's just look at what the benefit is. The NOTA system includes increased safety, the tail rotor being vulnerable. And like I said, if you hit something, hit the ground or hit a tree, then you can have a problem. You're going to spin. And when you're going to spin in a helicopter, it doesn't normally end up well. And because you hit the ground and the blades are still firing, the power plant is still moving, it will grind everything on its way down, including trees. And that's why I'm saying it doesn't normally end up well. Most people don't survive helicopter crashes more than the aircraft crashes. Okay, so this also reduces, I think, helicopters, they associate them with noise. Okay, that's the external noise. Again, this is reduced on helicopters. And NOTA equipped helicopters are among the quietest certified helicopters. Okay, so we've had a look at stability, but we have also looked at helicopter and also in terms of its stability as well. Shall we move on? Any questions? These guys are not playing today. They are understanding everything. If there are no questions, I will ask the questions then. No, not yet. Let's push a little bit, then we just go back to take our minds from this aircrafts, helicopters, and do some bit of equipment, then maybe we can come back again to aircraft as well. Okay. Now, I want you to consider an envelope, a normal envelope. When you're buying it, when you want to send something in an envelope, first you've got the small size envelope, you've got the medium size envelope, you've got the big size envelope, you've got the extra large envelopes. Okay. So if you want to send a big letter or a pile of documents, if you try and fit them in the small envelope, they won't fit. No matter how much you try or swear, it's simply not gonna fit. Because the dimensions just do not fit in that envelope. Okay. However, if you fit also a very small letter and an extra large, it will fit, but it will be just playing up and down in that envelope. Now, I don't know what's making Charmaine so excitable. Well, we're talking about envelopes, and big envelopes and small envelopes. So what we want is to match the size of the envelope with its contents. I'll try to word this very carefully now. With its contents. Now, we have to be very careful here. We are fitted in an envelope to such an extent that there is very little movement, but there's got to be a little bit a little bit of movement here and there. It's very difficult to fill the whole envelope, around all the corners. So there's still going to be some slight movement, right? That's allowed. Mhm. But they're not going to be excessive. Now imagine a small letter in a big envelope. Okay, it's just going to be moving right around that. Yeah. So again, this is what I want you to understand about the flight envelope. We take the whole aircraft as it is. Okay, imagine that we are fitting it in an envelope. It must fit all the time. If it goes slightly outside of that, then we got a problem. Something can easily happen. And it's not very easy to bring it back into that envelope. That's where the problem is. Envelopes. Who knew that envelopes can be this exciting? So several factors are important, such as weight. So we are putting in that envelope weight, speed, the flight level. But again, we have to take into consideration things like air temperature, density as well. But also the fuel capacity, which is then also referred to as the endurance. How far on these conditions can we continue flying? All those things will then fit into the flight envelope. If we increase the weight without making proper calculations, who thinks there's a good chance that we can go outside of the weight, outside of the envelope? Or is it not going to be affected? You can just show by your emojis, since you're now already experts in emojis. It won't? Johan, is weight going to be a factor?
Weight is a big factor.
A big factor.
Yeah? Yes.
And it can be a negative or it can be a positive, isn't it?
Yes.
Yeah. The less weight, the more you can play around in the envelope.
Yep.
What about the speed? Maria?
Sorry. So the speed, the faster you go, like it said, I'll recap.
So the faster you go?
The faster you go, the more limitations it has, if I'm correct.
I'm trying to figure out. You're on the right track, but I'm trying to figure out whether the way you've put it is enough. Now, it's not really about the faster you go. It's about how fast I think you can go without things going haywire.
Yeah.
Uh-huh.
Because the density and the forces.
Yeah, and the weight. The forces, you're right, yeah. In this case, we'll just call it the weight that the aircraft has got, and then at what level as well, the density, yeah, absolutely, and the temperatures as well. Okay. So whatever we do here with this envelope here, we must then say we've got enough to go flying without fearing for our endurance. We can still take off outside of this envelope, maybe, but maybe we will not reach our destination. So as an aircraft is flying, it's adjusting its weight, it's adjusting its speed, it's adjusting its flight level in terms of also air temperature and density. So what we are saying here, if it's weighing heavier, then you might not be able to have as much speed. But as you are flying and as you are getting rid of more and more passengers, you become lighter. Once you become lighter, then you can increase your speed. But obviously, it's not passengers you're going to get rid of, isn't it? It's as you burn fuel. That's one of the variables in an aircraft. As you're flying, you're burning fuel, so you're getting lighter. As you get lighter, you can increase your performance in terms of speed. You can also go higher as well, irrespective of the air temperatures and the densities. Naturally, you can go higher, and then you based on this now, you can choose the best level and also the best speed for yourself. So when we were doing flight planning, you notice there are points where there will be change in speed, change in levels. It's because now you are allowed to do that within that envelope without causing any harm, any structural damage to the aircraft, the aerodynamics of the aircraft, and also not negatively affecting your fuel endurance. If you wanted to go on full thrust all the way, that's fine. But you might not get there where you're going. Or you might get there, but when you reach there, you do not have enough fuel for diversion. If everyone's clear with this envelope thing, we shall call it an envelope thing because we are trying to adjust something into, great. Now let's have a look at what the notes say. Flight envelope, 200 tons, flight level 300. You already have a maximum speed, which is here, but this is not the maximum speed at 200 tons. This is what the aircraft is designed to do under certain conditions where the weight is not that heavy, okay, and that kind of thing, okay, and also in ISA atmosphere as well. Okay, but we are not always going to operate at maximum speed, although we would want to. So those factors there will tell us what speed is best to operate at when at this level. So the speed here, you can see it's very short speed range between the low speed, high speed. Jermaine, what will happen if you go below the low speed? What do you think will happen if you go below the low speed at level 300? Anyone wants to give that a try?
The aircraft will stall.
Yeah, it's actually written here, you stall. But again, Patrick, since you're the one who started talking about stalling, from what we mentioned today, what causes this stall?
Not enough lift going over the wing, not enough wind force. What? Wind going over the wings, the aerofoil, sorry, to provide enough lift.
We distort the whole factor in terms of how much dynamic pressure equals static pressure that the aircraft will get. And don't forget, the lift is not only on wings, it's also on the entire aircraft itself. Okay. Now, what if we go high speed? What most likely will happen? Again, we distort the airflow as well, and then we might also end up in a stall. But in some cases as well, this can also cause we might get away with a stall, but this might also cause structural damage to the aircraft because it's not meant for those kind of activities. So far, so good? I think so. Now let's look at 300. We've managed to burn fuel. Now we are down to 170 tons. Now we can operate at the operational maximum speed level up to that, okay? And here, but if you exceed the maximum, now you're going into a stall zone again. And this one definitely is what would normally cause most structural damage. But look here, because it's lighter now, look, within that envelope, we are able to fly. Our range here becomes more. We can fly slightly slower than we were doing at 200 tons and still we don't fall off the sky, but we can also increase. So it gives us much choice to operate within this whole range here. So speed range then increases as the weight decreases. Let's look at now, how high can you go? The flight level is also a factor. For the same weight, the speed range increases as the flight level decreases. At level 350, look, our options are very minimal. Still at 170 tons, but we've just descended to 300. It gives us more range we can work in. And this is from the same weight. So operating higher up there, it tells us because of the lower density, the lower temperatures, we are able to maneuver very little to remain within the envelope. You remember we mentioned earlier on, even when you're doing speed control, there is not much you can do in terms of speed. It's point something, 0.0 something you can do at a time. Because of this limitation here, because of the level which they are flying, and because this is because of the type of atmosphere they are flying. If an aircraft is climbing from 350 to 370 and tell it to expedite climb, he's going to acknowledge, but he's not going to be doing much more than 80 feet per minute, even if he wanted to. The aircraft performance would just not allow you in terms of the density, in terms of the pressure up there as well. So far, so good. But if you've been lower, you can do, because it's more dense, your range increases. Okay. So what is a ceiling? Ceiling is the highest vertical distance that an aircraft can reach. For a given weight, an aircraft is an absolute operational ceiling. You can't go beyond the absolute. No, I'm not saying you can't. You shouldn't go beyond the absolute operational ceiling. You can go, and then some edge will happen. Like you can even get structural damage to an aircraft. The specific range is the distance covered with a given quantity of fuel. For a given weight, there is a speed where the specific range is maximum. This is what you have to pick up now so that you got the best benefit out of the fuel that you have. A specific range which you come up with. Above this speed, the flight time will reduce, but the specific range will also reduce. So you might get there, earlier, but you might not have enough fuel if you go to divert. Flight tests for the aircraft which will determine the flight envelope to establish maximum speed, minimum and store speeds, the ceiling, then the critical angle of attack, then the maximum rate of climb. Let's look at those last two. Critical angle of attack. What is critical angle of attack? If you are to use in your own words. Hakim. Or anyone else can just jump in there. Do we remember what critical angle of attack is?
Oliver, we're getting network.
Sorry?
We are getting network issues.
Echo.
Network.
So am I lagging?
Yeah, you were lagging a bit since before.
Sorry?
It's on and off. You were lagging, but it's on and off. It comes and goes.
Okay. When that happens, can someone just raise a hand or just shout, yeah? Then I
Roger.
can sort of slow down. Is it better now?
Yeah, it's good now.
Okay. It could be I moved my head too much as well. I
No,
get
it's not
excited.
you, I think it's the SCA network.
Oh, is it? Okay. Anyway, we'll take note of this and see if it starts affecting, then we will have to get someone to
You come
fix.
back to Seychelles?
Yeah. Because what I don't want to do is to ask them if it's usable, to ask them to come and work on it, because it might stop working. It sounds mean, but that's the truth. So,
Best option.
critical angle of attack. What are we talking about here?
The angle which the aircraft will stall.
Yeah, if it goes beyond that, then you are going into the dangerous zone of storm. So, the critical angle of attack, is it going to be bigger or smaller when you are flying higher?
Smaller.
It's going to be very small. Okay, remember, it's less dense there. Okay, less pressure, and it's colder. Okay, so maximum rate of climb as well. In aircraft, we have a maximum rate of climb for especially at a particular given condition in terms of weight and things like that. So the maximum rate of climb, the best rate of climb for an aircraft is going to be when it's just taking off. True?
True.
Yeah. And as it climbs, it starts slowing down the rate of climb because it becomes less dense, so you can start getting less lift. But again, you can't go beyond the critical angle of attack because then you stall. But what it tells us also, once you reach these levels like 350, 370, your maximum rate of climb is going to reduce drastically, almost to crawling speed. Yeah, rate of climb. Okay. So you have to be careful if you are using that separation. Remember, level vacated can be allocated to the next aircraft. You have to be very careful up there, especially if the aircraft are one on top of the other or too close in trail. There are 7 categories of aircraft which may further be divided into 2 or more classes. So we've got single engine land class, multi-engine land class, multi-engine C class. I think we did a bit of this a bit earlier on as well, okay? And you remember how you can abbreviate it as well. In the rotor category, you've got the helicopter class, then you also have the gyroplane. Then the power lifted category, you've got the glider, which is lighter than air category, airships, and again, someone's favorite, the balloons. Then you got the powered parachute category. This is powered parachute land class, powered parachute C class, and weight shifted control aircraft categories, weight shift control land, weight shift control C. The ICAO wake turbulence category is entered in the appropriate single character wake turbulence category indicator, item 9 of the flight plan form. It is based on the maximum certified takeoff mass. What do we use? We use the MCTO, maximum certified takeoff mass. I think it's at the MTO rather than the MCTO. Hello? Patrick? How now?
Oliver, could you slow down a bit? It's like
We're lagging.
Okay.
Yeah, you were lagging there a bit.
Okay. Let's look at the ICAO wake turbulence
All
category.
good now.
1.5.
Item 9 of the model of flight plan.
So we're lagging.
Lagging a lot, yeah? Mhm. Let me do something else here.
It's okay.
Yeah, let me just take off this as well. And no one is on video right now. Okay. Is it better now?
4.5, yeah.
Okay. ICAO wake turbulence category. It's there on item 9 of your flight plan, based on the maximum takeoff weight or takeoff mass. Again, I think we've done these ones as well. Okay, that will be the same. Now, approach categories. Here we're looking at aircraft in the approach phase. We've got categories A up to E. Okay, and these are the range of speeds. 90 to 150, 120 to 180 for B. Again, for C, it's 160 to 240, and 185 to 250, 185 to 250. Okay, the range again for the final. So we're divided here into, sorry. If I click my mouse here, things start happening. So here we've got the initial approach and reversal and rest track procedures. So initial approach is when an aircraft is still coming in and not yet established in the hold. This will be the range. When now the aircraft is on final approach, the range is now further reduced. When cycling, I think you all now remember what cycling is. These are the cycling speeds. And these are maximum, so they can cycle at lower. So look at class E and D. It's cycling at a very high speed. This is why I've always encouraged you not to call it a circuit and just call it what it is. It is cycling. It doesn't, it cannot look anything like that circuit if an aircraft is flying at 200 to 240 knots. Then intermediate missed approach, then maximum speed on final missed approach. Okay, so you can see when they're doing the missed approach, they are pulling up and then they are also increasing their speed so that they can then gain momentum. Charmaine. Lagging. Is it still lagging? Charmaine? Patrick, what's happening? Sorry?
Hi.
Is it still lagging?
Yeah. No, I can hear you now.
Okay, so I want you to appreciate what's happening at missed approach. Look at the increase now to gain height in terms of speed. So your reaction time, especially for large jet aircraft and airliner jets, is very, very little before you can advise approach that the aircraft is going around, because it's increasing to that height. It needs to be sent over to approach as soon as possible. There is not much you can do with an aircraft that is flying at 240 knots indicated. Now, are you required to know this whole range? No. Are you required to know where to find it if you need it? Yes. Is any part of this going to be examined? Yes. Will I tell you which part is going to be examined? Yes. And that's what you concentrate on. Approach speed, which is translated as VAT, the criterion taken into consideration for the assignment of an aircraft, two specific categories: indicated airspeed at the runway threshold, VAT, while in the normal landing configuration. And again, we have to take into consideration the maximum mass, landing mass. This speed is defined to equal or greater the stall speed multiplied by 1.3. So this is important for you to understand how this is calculated. VS multiplied by 1.3 or stall speed multiplied by 1.23. Just know the formula. You will not be expected to make those calculations because it's already done for you. But you must know how it was derived. Yeah, we'll finish off this and then we will go for our lunch break. All commercial aircraft must meet the ICAO noise certification standards. We know there is environmentalists. We know they don't like they don't like aircraft. They don't like airports unless they are flying for their meetings all over the world. Okay. So, and why we don't also like the noise is when we sleeping, we don't want aircraft or helicopters flying past our bedrooms, especially. So there has to be a balance with the requirement for aircraft to be able to land and take off, and also with, however, causing very, the minimum amount of noise damage. So the balanced approach concept of aircraft noise management comprises of 4 principles, which is reduction of noise, aircraft noise at source, land use planning and management. You shouldn't put your final approach right overhead the most populated area. Noise abatement operational procedures. If you have an aircraft that is departing and going straight overhead houses, turning left, sorry, or right into where there's residential buildings or city, you might have to have yeah. So sometimes an airport will have to come with what we call a noise abatement procedure. I think what we'll do is let's come back and finish this after lunch. Okay. But before you go on lunch, what I want is a report in terms of the performance this morning. This morning, was it okay? So it just started now. So, yeah. So
Yeah, this morning was fine.
Was fine, yeah? Okay. Can you ask someone what during your lunch, the technicians, just to have a quick look? But maybe, no, leave it. Let's see how it behaves in the afternoon. Okay?
Okay.
Then what you can do is before you leave, I'll ask you to leave a little bit earlier so that it gives them time to do whatever their tests are. Okay? Yeah. Let's go for lunch and then we come back. Shall we do 45 minutes again or do one more? Okay, let's just come back at past. Let's make it easier.
All right, okay.
Yeah,
Welcome.
past. Yeah.